Yes, sir. It's visible, sir.
Okay. Up to 4:30 now? 4:30? What is the
Yes, sir.
timing?
Yes, sir. Now it's like 3:50.
Okay. Okay.
4:30 we can close
Okay.
it.
Okay.
Yes, sir.
Okay.
Thank you,
Okay.
sir.
See, if you have any doubt, in between you can raise. Okay. So this section, second section, terahertz source and detectors. Okay. First, source and detectors topic. Actually, up to now, at this in this electromagnetic spectrum, in this electromagnetic spectrum, this frequency only none of them has utilized properly. Before that, long back also they have identified this frequency. But the only drawback they found out no source and detectors. Source and detector is very tedious. Okay, so that's why. Sorry for the interruption. Wait. So that's why they didn't focus much about the terahertz waves. After that, they have found out that source and directions are there. Okay, so now all are moving to the terahertz because of it offers that high data rate, high speed. Okay, high speed to be possible in terahertz. That's why that 6G mostly we are using terahertz communications. That is a real thing. Okay, so terahertz sources and detectors. Terahertz sources and detectors. The main thing is focused on this terahertz waves, which is the terahertz waves spanning 0.1 to 10 terahertz exist between micro and infrared frequencies because already the electromagnetic spectrums structures are there. But this particular frequency, none of them have not concentrated. Okay, okay, not concentrated now because of the source and director complications only. So between this microwave and infrared frequencies, okay, these spectrums holds immense potential for wireless communication uh, in terms of security, medical diagnostics, and quantum sensing. However, generating and directing terahertz waves efficiently has been historically challenging due to the terahertz gap. Okay, the missing waves. Some literatures they mentioned that missing waves after they have detected. Okay, terahertz gap, where conventional microwave and optical technologies fall to perform optimally. See, actually, this detailed history, working principle, and real-world applications we can detect along to the terahertz sources and detectors. That the history and evolution of terahertz sources, early development actually in 20th century, I think 1864, Maxwell predicted electromagnetic waves, okay, including terahertz waves. Maxwell is the that is we used to say that Maxwell, James Clerk Maxwell, this Echo Maxwell in the 18 terahertz, terahertz waves, including terahertz. Actually, that after that, Chandra Bose generates millimeter waves. Maxwell predicts electromagnetic waves, including terahertz waves. In 19, I think 1864, okay, 1894, Jagadish Chandra Bose generates millimeter waves close to terahertz using a point conduct semiconductor detectors. During the 1920s and 1950s, infrared and microwave technologies improved, but terahertz generations remains inefficient due to lack of compact and high power sources. Because of that compact sources, it was not developed. Okay, lack of sources. So the breakthrough of terahertz sources during 1960 to 2000s. In 1960s, gas lasers CO2 and NH2 generates continuous terahertz waves. In 1970s, BW, which means backward wave oscillators, became popular but are large and require high voltage. During 1980s, PCA, photoconductive antennas and nonlinear optics into pulsed terahertz generations. In 1994, Terahertz time domain spectroscopy revolutionizes Terahertz imaging and spectroscopies. In 2002, quantum cascade lasers are developed, offering compact and powerful Terahertz sources. So modern terahertz sources at present we are using that plasma-based terahertz sources in 2010 provides broadband high power emission. In 2020 we are using that AI assisted meta surface based terahertz sources enhanced beam shaping and efficiency. Okay, so source types the types of terahertz sources and their applications is mentioned in based upon that different source photoconductive antenna, which is used to generate terahertz and which is used to detect that terahertz. Okay, so photoconductive antenna. It works under the principle of femtosecond laser excite semiconductor antenna to emit terahertz pulses in the range of zero point 0.1 to 3 terahertz. Mainly, that applications includes medical imaging and spectroscopy, security scanning. Okay, these are the general things for that sources. Okay, sources of terahertz. So terahertz detectors and the sources are crucial component terahertz technology, enabling applications in the imaging, spectroscopy, communication, and the security screening. So these are the things, types of nonlinear devices available. This is a basic for understanding that source and detectors. I think you are well aware of this about that types of nonlinear devices, diodes, transistors, and nonlinear oscillators, and variegated diodes. By using this only, we are generating the terahertz and optical nonlinear devices, nonlinear optical crystals, optical carrier effect devices, photoconductive antenna, semiconductor optical amplifier. These are the optical nonlinear devices. Okay, so uh, electronic nonlinear devices. By using the electronic nonlinear devices, A, and this one B, optical nonlinear devices, we can generate. Okay, okay. So we know about that. Yes. So first terahertz sources. This one. Terahertz sources generate radiation in the frequency range of zero point 0.1 to 10 terahertz. The choice of source depends on the required power, frequency range, and application. And common terahertz sources include photonic sources. Photonic sources, which includes a photoconductive antenna, which uses ultra-fast lasers to excite charges carriers in a semiconductors to generate pulses, terahertz radiations, and optical rectification. Nonlinear optical process in materials like ZNTA and GAP to generate terahertz waves using femtosecond lasers, and DFG, different frequency generation, uses two laser sources with different frequencies in nonlinear crystals to generate terahertz waves. These are the photonic sources which used to uh, generate that terahertz. This one is the electronic sources by using the guided and impact diodes, which operates in the terahertz gigahertz range, but can be extended into the lower terahertz range with multipliers and harmonic multipliers, extend micro frequencies into the terahertz range using nonlinear devices and quantum cascade lasers, semiconductor lasers operating at mid and far infrared wavelength useful for high power continuous wave terahertz generation. By means of electronic sources, we can generate. And free electron based sources. Free electron lasers provide high power tunable terahertz radiation using relativistic electron beam in magnetic field, and synchrotron radiation generates broadband terahertz radiation from particle oscillators, and backward wave oscillators operate based on electron beam interaction in slow wave structures. And terahertz detectors, which measures the terahertz radiation's intensity, phase, or facial characteristics. The selection depends on sensitivity, bandwidth, and the direction mechanism. Okay, these are the source and detectors we are using. And detectors, we can say that thermal detectors, bolometers, which uses the measures the radiation by detecting temperatures and changes in superconducting or semiconductor materials, and pyroelectric detectors, which uses temperatures induce changes in polarization materials like LATO3 to detect terahertz radiations, and Golay cells, which measures radiation by detecting pressure changes in a gas cell due to thermal expansions. And semiconductor-based detector, Schottky diode and FIT, they are using for detecting the terahertz sources. And photonic detectors, electro-optic sampling and photoconductive antenna they are using. So any one of the source and detectors with the mathematical analysis we are going to discuss. Okay, so these are the things various types available. Okay, many types are available because of that only drawbacks for generating and detecting terahertz waves efficiently has been historically challenging due to the terahertz gaps where conventional microwave and optical technologies fall to perform optimally. Okay, that is a thing we are facing. Now more sources and detectors are available. So one of the sources and detectors we are taking and with mathematical expressions we are going to see how it generated and detected. Superconducting detectors. Superconducting hot electron bolometers, 12 sensitive detectors for low temperature applications, and Josephine junction detectors use quantum effects and superconducting. These are the sources which used to generate that terahertz and detectors used to detect the terahertz signal with high precision. So mainly that application of terahertz detectors and sources are depend upon that in biomedical imaging, security screening, wireless communication, material characterization, astrophysics. Okay, so uh, yes. So this one, that example, important example of the hertz emitters and detector based on photoconduction. So here I have chosen that terahertz emitters and for detector based on PCA, photoconductive antenna. So photoconductive antenna is used to generate the terahertz, okay, frequency. So photoconductive antenna are among the most efficient and widely used methods for generating and detecting terahertz radiation. This cooperation is based on ultra-fast photoconductive in semiconductor material excited by femtosecond laser pulses, peak performance aspect of photoconductive antenna based on terahertz emitters and detectors. How it works? Emission from photoconductive antenna. A photoconductive antenna emitter consists of a semiconductor material with metallic electrodes forming a dipole antenna. Okay, a 50-second laser pulse excites electron pulse from the semiconductor. A bias voltage applied across the electrode. Yes, is it audible? Is it audible?
Yes, sir, it's audible, sir.
Okay, okay. So a bias voltage applied across the electrodes oscillates this charge carrier generating transmission photocurrent, and this rapid change in current produces broadband terahertz radiation. Okay, so here the key components of generating that terahertz, this is semiconductor materials. We have to choose that low temperatures GAS. Okay, GAS for higher efficiency and electrode structures, dipole and interdigitated design to optimize emission characters and bias voltage and femtosecond lasers. An enhancement of high-performance terahertz emissions include the antenna design, aperture load, plasmonic PCA, and antenna arrays. Okay, so here before that, the slides are visible now.
Yes, sir.
Okay. So actually, we know that terahertz radiation and these electromagnetic radiations, whose these frequencies lies between the microwave and infrared regions of the spectrum. Okay, we can't see the terahertz radiation, but we can feel its warmth as it shares its spectrum with far infrared radiations. Naturally, I think terahertz radiations fills up the space of our everyday life. Yet this part of the electromagnetic spectrum remains the least explored regions, mainly due to the technical difficulties involved in making efficient and compact terahertz sources and detectors. The lack of suitable technology led to the Terahertz brand being called the Terahertz gap. Okay, this technological gap has been rapidly diminishing for the last 2 decades. Optical technologies have made tremendous advances from the high frequency side, while microwave technologies encroach from the low frequency side. Okay, so these two fellows, uh, high frequency side and the micro low frequency sides, are occupying these things. Uh, only controlled this Terahertz band. Okay, so now that source and directors are easily we can generate. That is technological advancement in optics and electronics have resulted in many different types of terahertz sources and sensors. Okay, so now it could be easily we can generate the terahertz source and directors. Terahertz direction schemes are largely classified as either coherent or incoherent techniques. The fundamental difference is that coherent direction measures both the amplitude and phase of the field, whereas incoherent direction measures the intensity. Coherent direction techniques are closely associated with the generation technique in that they share under different mechanism and key components. Okay, so for example, we can see this uh, uh, terahertz terahertz directors scheme. Uh, yes, yes. That one way of generating terahertz radiation is to exploit yes, okay, yeah, yeah, yeah. So this emission from photoconductive antenna, uh, yes, by using this, but this is a fundamental process of terahertz generations. Okay, this is one. Yeah, photoconductive antenna consists of, because this is the structures. Okay, working principle. PCA emitter consists of a semiconductor material and 50-second laser pulse excites electron hole pair in the semiconductor, and bias voltage applied across the electrode oscillates this charge carrier generating a transient photocurrent. This rapid change in current produces, because how we can generate na PCA emitter consists of a semiconductor material. Okay, photoconductive antenna conducts that semiconductor material. So 50-second laser pulse excites electron hole pair in the semiconductor. Okay, excites, and we are applying that bias voltage across the electrodes, which one oscillate the charges carriers generating a transient photocurrent. This photocurrent produces the terahertz radiations. So these are the key components: semiconductor material, electrode structures, bias voltage, and femto laser. We have to consider for enhancing performance terahertz emission, antenna design, aperture, and plasmonic and antenna arrays. These are the fundamental process in terahertz generations. This one, we know that general electromagnetic equation in matters. So a semiconductor conductor material, GAS with electrodes and ultra fast laser pulse that excites charge carriers, a bias voltage that oscillates that carrier generating a transient photocurrent, emission of terahertz radiation due to the time dependent photocurrent. The time dependent photocurrent. The terahertz radiation field is directly related to the time derivative of the photocurrent, H. Okay, heat release is directly related to the dj of the dt. Here, gt is the time dependent photocurrent density. This is a fundamental process of terahertz generation. So, pure dynamic and photocurrent generations. So, here, when an optical pulse of intensity I of t, I of t excites a photoconductive material which generates electron hole pair at a rate. Okay, this is one. So this is efficiency, uh, quantum efficiency of carrier generations, and H is photon energy of the incident laser. So this photocurrent density is given by G of t equal to Q n of t by d. So n of t is the time dependent carrier density. This is drift velocity. Since this drift velocity is related to the applied electric field, see applied electric fields, so we can write that Vd equal to nu E minus. So the Fourier transform, we are taking the Fourier transform on terahertz spectrum. The emitted terahertz spectrum is given by the Fourier transform, Pth of omega I omega j omega. So here j omega equal to this thing. Okay, this is a Gaussian optical pulses. I of t equal to I naught e power minus j t omega square. Okay, so here this shows the terahertz spectrum is broadband with a peak frequency determining the pulse duration, sigma and the carrier lifetime. So this terahertz spectrum is broadband with a peak frequency is determined by the pulse duration sigma. Okay, pulse duration sigma and lifetime tau. So the carrier mobility is mu. High mobility improves and definitely that mu. This one mu. Okay, mu. Higher mobility improves the terahertz generation efficiency and tau. Okay, tau. This one tau. Tau means carrier lifetime. The shorter lifetime broadens the terahertz spectrum and bias voltage E bias. Okay, E bias. Higher bias enhance the terahertz emissions and lesser pulse duration. Shorter pulse generate higher frequency terahertz waves. So the mathematical derivation of the terahertz radiations, so the emitted terahertz field is governed by Maxwell equations. The key relation follow from the time dependent photocurrent ETH d of E by dt, where Jt is the photo current dependence, Jt equal to T n of T. E is the T is the electron charge, and the n of T is the photogenerated carrier density, and Vt is the carrier drift velocities. Applying to the continuity equation for carrier generation and recombinations, we can get it. So here Gt is the carrier generation rate proportional to the laser pulse intensity, and tau is the carrier recombination time. So this is the, we assume one optical pulse with Gaussian shape, g of t equal to m naught by root 2 2 pi sigma e power minus r square by 2 sigma square, where sigma is the pulse speed, then the transient photocurrent can be written as g of t equal to qvd integration of g of t e power minus t by tau dt. So taking the derivative, we can take the derivative, the electric field will be here. So this result in short broadband terahertz pulses. The spectral bandwidth is designed by this 1 by t. Okay, 1 by t, and the laser pulse width sigma. Okay, this one. So enhance of high performance, how we can enhance utilize nanostructures to enhance local electric field and increase the carrier mobility, corresponding PCA, and aperture loaded PCAs, optimize antenna structures to improve terahertz wave propagation, and optimize the electrode geometry. Clock periodic design to increase the radiation efficiency. And the terahertz direction. So before that, we had seen that by using the PCA, we can generate that source. And how we can detect by using that photoconductivity antenna. The working principle of this photoconductivity antenna would be the PCA detector operates similarly to an emitter but without an applied biases. Incoming terahertz radiation induces an oscillating electric field across the antenna. When a femtosecond laser pulse illuminates the semiconductor, it generates three carriers. So terahertz induced electric field oscillates this carrier, generating a photocurrent proportional to the terahertz field. So by measuring this current while varying the time delay of the pulse, the full time domain terahertz waveform is reconstructed. Okay. So what are the key components we have to consider for enhancing the detections? Same semiconductor and electrode structures as emitter, whatever we are using in that source, without a bias voltage. Lock-in detection system, which improves signal to noise ratio by using a modulated random signal, and time resolved measurement setups, also for broadband terahertz signal reconstructions, enhancement for high sensitive terahertz directions, antenna optimization, whether you can use that log periodic and Bauti design increase resolution efficiency, and low temperature ground semiconductors. Shorter carrier lifetimes improve temporal resolution, and the plasmonic enhancement nanostructures improve carrier generation response period, and resonant antenna arrays improve sensitivity for weak terahertz signals. So this is the mathematical model for terahertz radiation. The photocurrent directed in the PC is given by this one. Okay, this one. This is here. Mu is the carrier mobility. Uh, this is the incident terahertz field, ETH. It's incident terahertz field. This one is the photo generated carrier density. The carrier generation follows a Gaussian profile. Gaussian profile, we can write this equation n photo equal to n naught by root 2 by sigma uh, e power minus r square by 2 epsilon square. Here the directed current could be I directed equal to e terahertz q equal to e power r square by 2 sigma square. This shape of incident field allowing time domain spectroscopy measurement. Okay, so how we can enhance the terahertz director? Plasmonic PCS enhance light matter interaction and improve direction efficiency and antenna optimization. We can use log periodic and OTC antennas increase reception sensitivity and low temperature ground semiconductor reduce carrier lifetime to improve temporal resolutions. And the application of photoconductive antenna based terahertz emitters and detectors we can use in material characterization and imaging in the terahertz time domains spectroscopies and non-invasive imaging of tissues and biomolecules. Characters we can use in the biomedical imaging and security scanning we can use it and direction of explosives on the concealed objects and as well as high-speed wireless communication we can use this terahertz species enable ultra-fast data transfers. So the photoconductive antenna offers a compact, broadband, and efficient solution for the terahertz generation and directions. The derivations we have seen is the fundamental principles governing the operations, showing that the emitted terahertz field is proportional to the time derivative of the photocurrent, while the directed photocurrent is proportional to the terahertz field. Okay. So next, how we can generate? The first thing is for by using that photoconductive antenna, we can generate that source and we can detect it. Okay, that is the one type of method where we can consider the antenna parameters, antenna design categories, and light sources, optical laser light sources. We can enhance the performance of the PC. Next one is optical recreation for the terahertz generation. So optical rectifications is a second order nonlinear optical process which enables um, the generation of terahertz radiation. It occurs when an intense ultrafast laser pulse interacts with a nonlinear crystals, inducing a polarization that generates low frequency electromagnetic spheres in the terahertz ranges. See, actually, in history and the evolution of terahertz detectors, early direction methods and advanced terahertz detectors and modern terahertz detectors, it is step by step they have utilized and invented that so utilized that sources. Okay, the principle of optical rectification. See, this one. Uh, Optical rectification is the one method to produce the terahertz. Okay, it is act as a source. Okay, so optical rectification is closely related to different frequency generation, but differs in that both interacting optical frequencies originating from the same broadband laser pulses. Okay, ET. It is a second-order nonlinear effect described by the nonlinear polarization. So here, ET is the electric field of the input laser pulse, ET, because here differs in that both different from the, optical frequencies originate from the same broadband laser pulses. Okay, so epsilon naught is the primitive of the previous, and this one is the second order nonlinear accessibility. Since E of t consists of multiple frequency components, squaring the field result in a term at zero frequency and a term of low frequency terahertz. So E of square of t equal to summation of W1 of 2, summation of W1 of 2 W of t, E of omega 1, E of omega t equal to E power I omega 1 plus omega 2 t. So here omega 1 omega t results in a frequency within the terahertz range. For optical rectification, the relevant terms are those this term W1 of omega 1 omega 2 result in a frequency within the terahertz range. The generated terahertz field follows ETH omega. This one is this broadband band temperature pulses are identical and contain multiple frequency components that mix to produce terahertz radiations. Terahertz generation via optical rectifications that we have to consider phase matching condition. Phase matching is very important. For efficient terahertz generation, the phase matching condition must be satisfied this condition. So this is KTH is the wave vector of the generated terahertz fields, and this one are the wave vectors of the optical pump frequencies. Since terahertz and optical waves are very different reflective indices, like impedance matching, there is impedance 15 ohm. Okay, so like this here we have to use that. We have to use that different terahertz and optical waves, very different reflective indices in most nonlinear networks. Phase matching is often a challenge. To improve phase matching, we have to use tilted pulse fronts are used in nonlinear filters like lithium nitrate and quasi-phasing matching (QPM) techniques are used in periodically cold nonlinear materials. Okay, so here mathematical derivations of the terahertz field. You see, the terahertz field E terahertz obtained by solving Maxwell equation with the nonlinear. So this is the field square electric field transformed by c square to square e to 6 to t square. Okay, in this time. Using the nonlinear polarization Q2, can write that P of t. Okay, epsilon naught P square of t. So here KTH can write this one. So here L is the nonlinear crystal thickness and del K is the phase mismatch between minus k omega 1 minus k omega 2. The sim function accounts for phase matching efficiency, meaning terahertz output is highest when del k is zero, the efficiency will be high. So the choice of that nonlinear material, because here we are using that what, uh, so previously we used that yes, lithium niobate. Okay, lithium niobate. Okay, high efficiency, but requires pulse front tilting for phase matching. Common nonlinear materials used for optical rectification include zinc telluride, zinc telluride, which has that good phase matching for terahertz radiation. For detectors, we are using this one, widely used in terahertz spectroscopy, and gallium phosphate, which has a high nonlinear coefficient used for terahertz generation and direction, and lithium niobate, high efficiency but requires pulse front tilting for phase matching, and gallium arsenide. Gallium arsenide just at a high nonlinear coefficient but refers quasi phase matching. Okay, so that the gallium phosphate and gallium arsenide both are having that high nonlinear coefficient, and zinc telluride having that good phase matching. So, hmm, yes, application of optical rectification in terahertz technology, terahertz time domain spectroscopy. By using this, that material characterization and imaging and security screening, we can identify and nonlinear terahertz objects generation of high power Terahertz pulses for research. We can enable and we can develop it. And the non-invasive imaging using Terahertz radiation. Because of this safety property, we can use in the biomedical imaging. And optical rectification can generate high-speed Terahertz signals for because tera bits per second. Okay, for future wireless networks. So optical rectification is a fundamental method for terahertz generation, exploiting nonlinear polarization effect in materials with a strong second-order susceptibilities. The efficiency depends on the choice of this one. Nonlinear crystal. Is it audible?
Yes, sir.
Okay. Nonlinear crystal, phase matching, and input laser properties. Okay, this one while designing this one only. So that's why the nonlinear crystal. Here, types of nonlinear material we are choosing. No? Okay, nonlinear phase matching and input laser properties. Okay. And one more four slides. I have to slide. Yeah. Uh-huh. Yes, yes, right. I thought 2 minutes. Yes. One more slide. I am going to share. Yes. So this one previous electro-optic sampling. So here the principle of electro-optic sampling. Uh, previous electro-optic sampling is a powerful technique for detecting terahertz radiations. It utilises the Pascal's effect in which terahertz electric field induces fire fringes. Okay, in an electro-optic crystals, modulating the polarization state of co-propagating probe laser. This modulation is then measured using an optical detecting system. This is the one of the uh, detector. Okay, one of the detector sources. Principle of electro-optic sampling. The fundamental principle of EOS is based on the interaction between the terahertz field and an electro-optic crystals, where the terahertz fields modify the refractive index via the Michael's effect. The refractive index alters the polarization of the optical profiles, allowing the measurement of the terahertz field and okay. These are the electro-optic packet effects, Pascal's effect. When an electric field ETH is applied to an electro-optic crystal, it induces a change in the refractive index. According to this one, N is the refractive index of the optic crystals, R is the electro-optical coefficient. Is on the applied terahertz field. The change in refractive index modify the phase of an optical probe beamforming propagating through the crystals. Okay. So the derivation of the electric optic signal phase redirections induced by the terahertz fields. So the optical profiles experience a pulse redirections due to the gamma terahertz induced five ranges. Gamma equal to 2 by lambda del NL. Lambda is the optical probe wavelength and L is the thickness of the electro-optic crystals. So substituting del and here, the shape shift modify the polarization state of the probe beam, which is directed using a balanced photo detectors. Okay. So intensive measurement using a balanced detectors. This one. The probe beam is typically linearly polarized at 45 degree to the principal axis of the crystal, producing an electrically polarized output. So the transmitted intensity after a photograph plate and polishing beam splitter is given by this technique. The detected signal from a balanced photo detector which measures the difference between the two intensities. Okay. So here we are getting that the detected intensity directly proportional to the terahertz field, allowing for an accurate time domain measurement of the terahertz fields. Okay, intensity based directions. So the electric experimental setup for three-phase co-optic sampling. Optic sampling. The typical US setup includes terahertz pulses source generated via optical rectification in a non-linear crystal and electro-optic crystals. and filters in probe laser and photograph plate and polarizer and balance detectors, which measures the terahertz induced intensity. And advantage could be that non-contact, ultra-fast detection of terahertz pulses, broadband detection, phase-sensitive measurement, and application in material characterization and biomedical imaging, study of terahertz-induced nonlinear phenomena, and characterization of terahertz wave propagation. Okay, so uh, yes. The last one, broadband terahertz pulses. With this, we can conclude with this. Okay, with this topic. Ultra broadband terahertz pulses. Ultra broadband terahertz pulses are short duration electromagnetic pulses that cover a wide range of terahertz frequencies, typically 0.1 to 30 terahertz or beyond. These pulses are essential for applications in spectroscopy, imaging, and wireless communication due to their ability to resolve ultra-fast process and penetrate various materials. So how we can generate optical rectification in nonlinear crystals and photoconductive antennas and plasma-based terahertz generation, different frequencies generation in nonlinear media. Among this, optical replication and plasma-based terahertz generation for the broadest terahertz bandwidth. So this is the mathematical derivation of the terahertz pulse generations, time domain representation of an ultra broadband terahertz pulses. This one, A is the peak field amplitude and tau is the pulse duration. Omega naught is the central angular frequency and pi is the carrier angular phase. Okay, so we are taking the Fourier transform. This one we are getting this is the frequency domain representations for this equation. This Gaussian spectral profile indicates that a shorter time domain pulses result in a broader frequency spectrum, obviously that achieving ultra-broadband characters. And the optical rectification is of for ultra-broadband terahertz generations. This optical rectifications is an important method for generating broadband terahertz pulses. The nonlinear polarizations induced in a nonlinear crystal by femtosecond laser pulses. Here, that second order, this one is a second order nonlinear sensibility. That pumping, E-pump is a short pulse with a broad spectrum. Squaring it generates terahertz components for different frequency generations. This integral suggests that broadband optical pulse leads to a broad terahertz spectrum. Space matching already I focused this one. Phase matching condition was followed by the terahertz emissions. The efficient terahertz generation refers space matching ensures requiring the generated terahertz will consecutively interfere uh, where this one KTH and K are the wave vector of the terahertz and optical waves respectively. Since because this is optical, that one is terahertz. Okay, since the refractive index may be different, optical and terahertz frequencies large. Pulse front tilting or positive phase matching techniques are often used to optimize broadband generations. This is the terahertz pulse bandwidth and duration relationship. Okay. From Fourier theory, the relation between the temporal width tau and spectral delta del f for ultra short pulses given by the del f tau greater than 1 by 2 by 1 by 2 pi. For ideal Gaussian pulse, the minimum that is a TPP is time bandwidth product is del f tau equal to this one. This means shorter terahertz pulses inherently possesses a broader bandwidth. Ultra broadband terahertz pulses typically have durations below 100 femtosecond, leading to bandwidth exceeding beyond 10 terahertz. So application of this ultra broadband terahertz pulse generations is in TDS time domain spectroscopy, resolving molecular and lattice vibration materials and nonlinear terahertz optics, high field terahertz interaction with matter inducing nonlinear effects. And because of that high speed data transfer capacity, it uses in terahertz wireless communication at multi terahertz bandwidth and the non-invasive detection of biological tissues and concealed objects. So it uses in terahertz imaging and security screening. So ultra broadband terahertz pulses are generated using femtosecond laser sources via optical rectification, photoconductive antennas, or plasma interactions. And these mathematical derivations highlight that shorter pulses correspond to broader spectral bandwidth, making them ideal for high resolution spectroscopy and ultrastudies. So with this I conclude uh, my section. Okay, my two sections and important things means up to now we have discussed about the terahertz radiation and the element stations because terahertz playing that major role in the 6G technology. Because why we are using the terahertz communication? In first generation we can use only we can uh, I use that voice communication 2.4 kilobits per second, and second generations they transmitted at 64 kilobits per second. After that 1 megabits per second, then fourth generation gigabits per second, sorry, megabits per second, and fifth generation gigabits per second we achieved, and sixth generation terahertz bits per second. That means very high speed multimedia we can support. That means high throughput we can achieve with low latency. Okay, so number of bits transmitted, number of bits successfully received because it supports that high speed communications. Only problem is major problem is that part loss. By mitigating this, we can enjoy the benefit. And generating the source and the direct is complicated. That also the now easy process. So that's why we are studying about the terahertz radiation and delivery of radiation in first sections. That's what was. After that, the complicated issues, the complicated issue in terahertz communications. Okay, major issues in terahertz communication is that generation of source and the directors only. Okay, so that's why in second sections we have highlighted the terahertz directors and sources. So we have seen that uh,
Yes, it is audible.
Yes, sir. Now it's audible.
Right, right, right. Due to power issues here, that was disconnected. Anyway, okay. So here in terahertz detector and sources, we have seen ultra fast optics, terahertz emitters and detectors based on photoconductive antennas and optical rectification and free phase electro-optic sampling and ultra broadband terahertz pulses, terahertz radiation from electron oscillators and these are the important things we have highlighted in the second sections. So the major complications for steroid studies is direct and sources. These are the systems are available. So now easily we can utilize it and we can enjoy that benefit of steroid sources, and we can use benefit of terahertz. The radiation and element radiations are at the frontier of modern physics technology. Their application span in wireless communication and wherever we need it. So, by properly we are using that system now, we can enjoy the benefit of terahertz. Okay, so this development of terahertz sources and detectors has led to breakthroughs in wireless communication, security, medicine, and quantum technology. As now recently that AI developed AI and nanotechnology and quantum materials continue to evolve. The future of terrace technology promises faster, safer, and more efficient solution for next generation applications. Okay, thank you, thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you for joining us, sir. Thank you, sir.
Thank you. Thank you very much. Okay, we can complete.
Yes, sir.
Okay.